This question comes from Peter. If every person on Earth aimed a laser pointer at the moon at the same time, would it change color? Not if we used ordinary laser pointers. First, not everyone can see the moon at once, and we already learned how that goes. Most of the world's population lives between 0 and 120 east, so our best chance of illuminating the moon is when it's somewhere over the Arabian Sea. Let's pick a quarter moon at night so we can compare effects on the dark and lit sides. A typical red laser pointer is about 5 milliwatts, and a good one would have a tight enough beam to reach the moon, though it would spread out over a huge fraction of the surface when it arrives. Assume everyone can steady their aim and the light spreads evenly across the lunar surface. The result, nothing noticeable. It makes sense. Sunlight delivers a bit over a kilowatt per square meter to the moon and Earth. The moon's cross-sectional area is about 10 trillion square meters, so the bright half receives roughly 6 petawatts of sunlight. All the planet's 5 milliwatt lasers together only add about 30 megawatts, roughly 200 million times weaker than sunlight. There's no way we'd see that. What about more power? A 1-watt laser is extremely dangerous. It can blind you, burn skin, and start fires. There are legal limits on selling them in the US, though off-brand listings are abundant online. If we somehow bought 1-watt lasers for everyone, our combined illumination would be about half a lux on the moon's surface, roughly half as bright as moonlight here on Earth. Sunlight's 130,000 lux still drowns that out. If we step up to searchlights, the night sun used on helicopters at around 50,000 lumens, and focus them down with lenses to the moon's half-degree apparent size, our collective beam could provide about 20 lux on the moon. Twice the ambient light on the night side. Still, nothing noticeable on the day side. Upgrade again to IMAXable projectors, pairs of 30,000-watt water-cooled lamps, or the Luxor Hotel spotlight, and the effect remains tiny. At last, with enough focusing and power, the moon's brightness becomes visibly affected. But to truly match sunlight, we'd need enormous lasers. Imagine building megawatt-class visible lasers like the experimental megawatt infrared system once tested on a modified 747. Giving one to every person finally matches sunlight's brightness, but it draws about 5 petawatts of power, roughly double the world's average electricity use. If we went further and placed a megawatt laser on every square meter of Asia, we'd consume Earth's oil reserves in a couple of minutes. For those 2 minutes, the moon would shine as brightly as mid-morning sun, and by the end the lunar regolith would be glowing from heat. Take it to the extreme. The most powerful operational laser pulses, like those at Fusion Labs, produce hundreds of terawatts in nanosecond bursts. If somehow fired continuously and scaled up globally, the atmosphere would ionize into plasma and Earth's surface would ignite, killing us all. If we somehow prevented atmospheric interaction, the moon would still suffer. The lasers would vaporize lunar rock, creating a plasma cloud that eventually blocks the beams. As more energy is pumped in, that plasma gets so energetic that chunks blast off into space like a rocket exhaust. This laser ablation jet could push the moon out of Earth orbit in a few months. Once the moon is pushed out, its new eccentric solar orbit would be unstable. Eventually it might be slingshotted into the sun, ejected into the outer solar system, or slammed into another planet, possibly Earth. Given that scenario, we'd have brought it on ourselves. And that, finally, is enough power.